anybody know what a scalar is? Raise your hand if you know what a scalar is. Nobody? You guys are not going to pass the JE. So, what is a scalar? Well, essentially, it's just a value. Okay. Can anyone raise their hands? Does anyone know what a scalar is? Okay, maybe it's just a... Oh, okay, a few people, maybe. But it's not a majority of the audience, so I'm going to have to explain it. So, a scalar is essentially just one value. It's just something like 3 or 7 or 191. Can anyone give me a few more examples of a scalar they can think of? Anyone raise their hands if they want to answer that? Anyone? Raise your hand if you want to answer that question. I know, man. I'm trying to facilitate audience participation. So, if you could please just raise them high. No one can think of examples of a scalar from what I've given. Can everybody see the board? Oh, okay. There's one guy in the back over there, so... So a scalar is just a singular value. It can be anything on the real number line. It can be in this direction or in this direction. So it could be negative pi, or it could be e, or it can be the square root 2 to the square root 2th power. Doesn't matter what it is. That's what a scalar is. So, a scalar is just any real number. But now, let's move to the concept of a vector. Does anybody know what a vector is? Raise your hands. Okay, I see somebody. So, can you keep your hand raised so I know where you are? Okay. Let me see. Should be somewhere over there I was looking for, but we can work with it. So, it of course has magnitude and direction. And how do we describe the magnitude and direction? Well, the magnitude is just the length of the vector, and the direction is what angle it's pointed at with respect to the x-axis. So, we can actually specify these using the components of a vector. So, the components of a vector are essentially the lengths of the projections of the vector onto the x and y axes. So, this blue line right over here is the x component, and this green line right over here is the y component. So, we write it like this, x comma y. And of course, the length using the Pythagorean theorem is simply square root of x squared plus y squared, and this is simply arctan of y over x. So, we know what a vector is. At least we know what a vector in 2 dimensions is. But, in general, a vector is just any array of numbers. It can be a catalog. Of course, it can't be an infinite catalog, then that's just a set, not a vector. But it's just a catalog of numbers. 4, 7, 3. And the same number can, of course, repeat twice. Now, of course, this is an 8th dimensional vector, so obviously I can't draw it. But we all know what a 1-dimensional vector looks like. This is just a scalar. A 2-dimensional vector is something I've just demonstrated. And a 3-dimensional vector is quite easy to visualize as well. You just draw the 3 coordinate axes, x, y, and z. You get the x coordinate, you get the y coordinate, and you get the z coordinate. And that's the vector. So, this can keep going past the 3rd dimension into any dimension we want. So, the best way to specify a vector is just going to be v. And to show that it's a vector, we're going to draw a little arrow sign on top of it, because vectors usually look like arrows. So, This vector is just an array of numbers. Now, how do we know which, let's say we want one specific component of the vector. Like, for example, in the vector 2, 5, let's say this is vector v, we want to specifically obtain this number, 2. Does anyone know how we get that number? Anybody? Raise your hands. How do we denote the x component of a vector? This lecture is going to be a lot longer than I expected. Nobody knows? Come on, don't be scared to answer questions. It's not like you're going to be wrong all of the time, right? And of course, being wrong is anyway how you learn. Anybody? Oh, okay. Yeah, you have my.
In the rectangular coordinate system, we denote the x coordinate by using unit vector, which is I cap.
Yes, okay, that's a good start, I guess. But what I was more saying was, how do we get the 2 in specific? And of course, as he said, this can be denoted like this, but that's not going to apply to n dimensions. So instead, what we write this as is Vx. But here's the problem. Eventually, at some point, we're going to run out of letters. There are only 26 of them. So just use Greek letters. But there are only 24 of those. So just use Hebrew letters or something. But there are only 30 of those. At some point, we need to generalize it. So what's the only thing that doesn't run out? Numbers. So since the x component is the first component, we're going to denote it instead as v sub 1. You can sit down. Thank you.
I have a doubt.
Yes.
You are using a lot. You are using numbers a lot, but I don't know the actual meaning of actual definition of numbers. Can you please?
Okay, got it. So we have this vector 2, 5, which we are going to define in the coordinate plane. Of course, 2 is just going to be the x component right over here. And 5 is going to be the y component. Oh, by the way, a side question. What standard are these students in? Oh, okay. All right, sure. So, we have this vector right here, which goes 2 in the x direction and 5 in the y direction, right? So, then, if we want to access the x direction, we just have this component right over here, Vx. And here's what we're going to do, actually. Instead of using letters, which we all know run out super quickly, instead, we're going to use numbers. So, x is the first component. X is the first coordinate, so we're going to call it 1. And y is the second coordinate, so we're going to call it 2. So, Vx becomes V1, and Vy becomes V2. This is just so we can generalize it past the second and third dimension, into however many dimensions we want. Alright, so that's how we denote the component of a vector. But now I'm going to do a little bit of a switch in notation. Actually, I think it's best if we just stop at covariant and contravariant tensors instead of getting into calculus. So we have v right over here, our vector, and instead of using subscripts, we're going to use superscripts. And the reason for this is going to be apparent later, but just go along with it for now. This is going to be a superscript. So this is just going to be v1i plus v2j, if we're in 2 dimensions, of course. Or if we're in n dimensions, here's what we're going to do once again to generalize. Because I and j are the basis vectors in the second dimension. In the third dimension, it's k. But then, in, say, the 27th dimension, maybe you can use all the letters of the English alphabet, but you still have one basis vector left. What do you use then? So, instead, to generalize, we're once again going to be using numbers. I is going to be E1, J is going to be E2, and k is going to be E3, and so on and so forth. So we get V1 E1 plus V2 E2, and so on. So this is going to be, if we have just n components, we get Vn En, right? So this is going to be how we write any vector. So now what we're going to do is explain the concept of covariant and contravariant. Imagine temperature in a room. So imagine we have a room, and let's say it's hot at this side, and eventually it gets colder at this side. So what we're going to do is we're going to describe that temperature using a scalar field. A scalar field is essentially what happens is that every point in space is just assigned a scalar, a number. So if it's hot at this side of the room, the temperature as a scalar would be, say, 200. And then it goes down over here to maybe 190, and as it cools off, eventually over here it's going to be 0, and maybe even negative as we go even further. And of course, remember, they're not just at the lattice points, they're at everything in between as well. So, a scalar field is just a field that assigns a number to every point in space. So an example would be f of x comma y on the 2D plane is equal to 3x plus 2y. And of course, this is a scalar field. Why? Because you could just take any old number, any old point. Let's say we get 7 comma 2, for example. So if we plug in 7 comma 2 here, we get a scalar. And that scalar that we get out is going to be 25. 7 times 3 plus 2 times 2. So this just assigns a number to every point in space. And you may have seen any scalar field visualized as a surface or a three-dimensional function. I think I'm going too far, actually. I don't really know. So, a surface is just graphing in the three-dimensional coordinate plane, like this. So, as you can see, this is just a surface in our coordinate plane. I'm going to erase the in-between lines. Okay, great. So this is our surface. And now what does it do? Well, the height above the ground on the z-axis is just the scalar assigned to that point on the xy plane. Alright, so now imagine we take some random point on the surface, right? And let's say the value right over here is, I don't know, f of x1, x naught comma y naught. Now, what I'm going to do is I'm going to do a little sneaky thing. I'm going to go in some random direction, going to put a little differential there, going to take a tiny step called ds, and go to a new point. Here, the value is f of x1, y1. So now, all we're going to do is we're going to take the derivative. We're going to take f of x1 comma y1 minus f of x naught comma y naught divided by the magnitude of ds, which is, of course, you can calculate that from the Pythagorean theorem. And so, that's what we call a covariant vector, or a covector for short. It's just a vector with the magnitude of this derivative in the direction of ds. So, essentially, a contravariant vector is just a regular vector, the one with magnitude and direction we just talked about. And a covariant vector is essentially like taking the derivative of a scalar field. All that means is we have this field of numbers 1, 3, 5, 0, 7, 2, 6, 1, 4, 3, 1, 2, 3, 4, 5, and so on. and we go from some random point A to some random point that's just nearby, called B, and we measure the change in the scalar field between those 2 points. And as the magnitude of this vector approaches 0, we get to find the magnitude of the covariant vector. So this is essentially like the derivative over a contravariant vector. If you've ever taken calculus 3 or multivariable calculus, you'll find that it looks like partial of this function in some random direction, ds. So we're going to call that some vector, actually, v. And so that is what we call a directional derivative, also known as a covariant vector. So I have a feeling that if I go beyond this point, most of you won't understand. So this is where we're going to end with the notion of a contravariant vector and a covariant vector. So once again, just to review, a contravariant vector is just a vector, and just a regular vector, magnitude and direction, as others have said before. And a covariant vector is just a change in a surface, or a change in a scalar field. So I feel like I may have not considered the level of the audience in today's talk. So are there any doubts I can clear up in the audience? Does anyone have a question about what just occurred? Anybody? Yeah, I haven't got the audience talking, so. Alright, let's see. Is there any better way I can teach this? So, a covariant vector is a change in a scalar field. And what is a scalar field? Well, a scalar field is like temperature. Every point in a room has temperature, right? Tell me, does every point in a room have a temperature? Yes? Can you find some point in a room that doesn't have temperature? Louder? Louder? Good. Okay. So, that means that temperature is a scalar field. Now, how would you describe temperature? What is temperature? No, and not the physical definition. Is temperature a scalar, a vector, or something else? Anyone? Louder.
Scalar.
Good. Temperature is a scalar. It's just a number, like 37 degrees Celsius. That feels like the temperature in this room right now. So, every point in a room has temperature, and temperature is just a number. So a scalar field is just something which at every point assigns a number. Do you understand? Okay. So now, let's say in this relatively hot room, I take a tiny step from here right over to here. This is what we call a differential step. Here over to here. It's a very small step, and it gets even smaller as you go on. Does anybody in here know what a derivative is?
Yes.
Louder? No?
Yes.
Yes? Does anybody know what a derivative is? Anyone? No. I'm going to guess that's a no. So,
So, can you repeat the term?
does anybody here know what a derivative is? Yes or no?
I'm sorry, I don't know.
Okay. So, here's what a derivative is. Let's say we have a function. Yes? So, now, in that function, what we're going to do is we're going to take one point right over here and then another point right over here. Now, let's say this is x and this is x plus h. And this is f of x. Then the y-coordinate here is going to be f of x, and the y-coordinate here is going to be f of x plus h. So then what we're going to do is we're going to draw a secant line between these 2 points. Right? It's a line that goes through both of these points. And we're going to take the slope. Everybody here knows what the slope formula is, right? Okay, so can you guys tell me what's the slope of this red line? Okay, let's start from this. What is the slope? What is the slope formula?
It is the rate of change of y with respect to x.
Okay, so that means it's just going to be the change in y divided by the change in x, right? Good. So then the initial y value is f of x. The final y value is, anyone have an idea? Louder. Good. And we divide that by the difference between the final, which is x plus h, and what's the initial? Louder.
X.
Good. So then these two just cancel out, and we're left with what we call a derivative. But this isn't a derivative quite yet, because h is a number. But what we're going to do is, this number is going to get closer and closer to a certain point as h becomes closer and closer to 0. So in the same way, we're going to, instead of taking a little step, specifically in the x direction, as you can see we did here, we're going to take a little step in any direction we want. Like, let's say I choose that direction, right over there. I'm going to take a step in that direction, and then go back here. I can feel the temperature here, and then I can feel the temperature here. It's a very small change. So, what we're going to do is we're going to take f of, let's say we have the initial coordinates, plus our little differential vector dv minus the initial coordinates divided by that little change, dv. And the thing is, the direction of that vector is going to stay the same, but the magnitude is going to go from a large step like this to a very small step to an even smaller step, and eventually it's going to approach 0, just like 8. Hopefully I haven't lost anybody. So, that means that we're just going to take a very small step in any direction. We're going to record the change in temperature. Then we're going to divide that by the magnitude. And we're going to keep the magnitude getting smaller and smaller and smaller. And so, what we get out of this, the limit, is going to be the magnitude of our covariant vector. So, essentially, what we're doing is we're pointing in a direction, we're taking a very small step in it, and then we're recording the difference in temperature between here and our original position, which is of course very small. Then we divide the small change in temperature by the small change in by the small vector, specifically the magnitude of the small vector. And then once we get the value of that, we make our vector in the same direction, but instead of a big step, it's a small step. It becomes even smaller and smaller until the 2 points are virtually indistinguishable. Then the direction of our covector is parallel to our little ds, and our magnitude is equal to the limit of this. So, hopefully that's a bit more intuitive of a definition. All that it is recording how big a change is in temperature. So, if the temperature changes a lot between this side and that side, like let's say we have let's say we have a desert bordering snow, then if the temperature is really cold on this side and really hot on that side, then the derivative as we walk from here to there, the covector is going to be very large. But if the temperature is generally the same all around, it's 30 degrees Celsius right over here, and it's 30 degrees Celsius over here as well, then there's not going to be any covector. The covector's magnitude is going to be 0 because there was no change. There is no derivative. Does everybody understand that? Okay, so that's where we're going to end off today. So that's contravariant and covariant vectors. Thank you everybody so much, and I hope you definitely learned something from this lecture.
Who is the president? Is it lady? Yeah, so proud of you, no, girls. So now question session starts from you. Your name, your class, and ask your questions accordingly. Thank you.
My name is Nishat Tasneem. I'm from 11th standard. And sir, my question is quite insignificant compared to whatever you know. We don't have very much knowledge about dimensions. We're just learning very basic things about 1D, 2D, and 3D. But there are around 26 dimensions, or maybe 20. I am not much. No.
Yeah, I can.
I just wanted a little brief about what are dimensions. Like from 4D onwards, like we can we know about the X, Y, and Z axis of 3D. So when it will be 4D, what is the extra axis that will come, and just a little briefing about dimensions and all.
Of course. So let's say I pick up this tissue box right over here. So then this tissue box looks like this, right? So we've got this tissue box looks like this. And of course, I'm the best artist in generations, so you can obviously tell this is a tissue box. So this is the length, this is the width, and this is the height. All we mean by 3 dimensions is 3 metrics that we use to specify the size of any object. So, using the length, width, and height, we can say that this object has some sort of size. And the reason we use them perpendicularly is very simple and makes our volume and area calculations very easy. So if we have a sheet of paper, usually the thickness is negligible. So we talk about the 2 metrics that we measure it with. We measure it via the width and via the height. And so if we're in 4 dimensions, then we use 4 metrics to measure it. But of course, we haven't come across any objects that need that in the real world. And so, since we don't need it in the real world, we can't imagine what it would look like on a sheet of paper or a smartboard. It's a very nice question. And actually, the reason I said, what if we're in the 27th dimension, which apparently seems a little bit confusing, this essentially just means that we have an object that needs 27 perpendicular axes to measure. Of course, there's nothing like that in real life, and there probably never will be. But this allows us to generalize any vector. Because the vectors that we have in our life usually have 2 components, or maybe 3 components. But it turns out, in general relativity, most vectors have 4 components because they have to account for time. And if we were doing general relativity in any other dimension, which seems to be useful for other applications like string theory, we could have even more than 4 dimensions, maybe even 12. So, we just generalize any vector because it makes things easier for us to do in higher dimensions, which we often need to do when considering theories that utilize higher dimensions. Of course, we already can see 3D in real life, but when it comes to 4D, which is what general relativity often uses, we can't actually visualize that. So we simply have to generalize it. When it comes to, for example, string theory, which has 11 dimensions, or so I've heard, then we need to generalize that even more, because that is beyond human imagination. And finally, when it comes to the axis that is beyond X, Y, and Z in 4th dimensions, doesn't have an official name, and any official name isn't important, but most people opt to call it W. So thank you for the question. It's very interesting.
Thank you, sir.
Thank you for your, nice questions, Rish. Next questions, your name and class. Oh, that's it. Okay, please. Oh, from this one. Okay. One from this side, one from this side. Okay. So next questions, your name and class.
Good afternoon, sir. I am Mohammad Muaz Laskar of 12th standard. My question is basically related to physics.
Another physics question. No, it's okay.
We all dream. we see some visuals. My question is, how do blind people dream? Do they dream, or how do they dream? If they dream, they need to see something, and if they can't see something, how they see something?
Well, that's more of a psychological question, but I guess that blind people dream because obviously, dreaming isn't using your retinas, and most blind people don't just completely see black. Instead, they have like clouds in front of their eyes, for example, that don't allow them to see anything except their peripheral vision. So thus, they're legally blind. And in that specific case, we call it cataracts. But in our dreams, we obviously aren't using our real eyes. So instead, we're just using our imagination. Of course, I don't exactly know how dreams operate, and I believe the leading psychologists don't know either. But I don't think blind people or people with cataracts dream with little clouds in front of their eyes. Although you'd obviously have to ask people with
Does that mean
cataracts.
that they only see the clouds in their dreams, or they don't dream?
Well, you'd have to ask a blind person because I'm not blind. Thank you.
Next,
Math and physics.
math and physics, not psychology. Please, specially I will encourage to ask questions from mathematics.
Hello, sir. My name is Shabana Nazmin Chaudhary, and I am in 11th standard currently. My question is that the theory of relativity is, of course, very complex and a lot more than we expect it to be. And how would you just give a brief idea about relativity to a person who doesn't have much knowledge about it?
Okay, sure. So essentially, what relativity does is it's all based around what we call the field equation. And this field equation is just an equation with a bunch of variables. And most of these variables are just matrices of some random numbers. And these numbers encode everything from the electric field to the magnetic field to mass to energy and so on and so forth. So they're like little encodings of everything that's going on in the universe around us. And essentially, all of these numbers and matrices surround one specific variable, which we call the metric tensor. And this metric tensor is actually a matrix. This matrix is just describing how space-time curves. And in response to space-time curving, objects are going to roll around. In response to objects rolling around, space-time is going to curve due to their own mass. And so, this is all equal to a proportionality constant times all of the mass in the universe. So essentially, all that relativity is saying is we have an encoding of all the information in our universe, and the variable we have to solve for is the curvature of space-time. Now, in practice, this is impossible to solve without computers, and even with computers, we can't really get close to encoding our entire universe. But it has proven to be correct through a few tests of smaller equations. So, I don't know if that's a good overview of relativity, but that's basically what I can give. Thank you.
Thank you, sir.
Yeah, nice questions. Now, from the boys group. So let's
Do the summation of this.
Ooh, that's a hard one. Okay, got minus 1/2 plus 1/3 minus. Oh wait, no, never mind. That's pretty easy, I think. Okay, so what I saw there was minus 1/2. Oh my, okay. Minus 1/2 plus 1/3 minus 1/4 plus 1/5 minus 1/6 plus 1/7 ... So here's my thoughts about solving this equation. So, of course, you can already tell, and here's what I'm going to do. First, I'm going to add a 1 to this side, and let's say this is x. We're going to add a 1 to this side. And so, 1 minus 1/2 plus 1/3 minus 1/4 plus 1/5 minus 1/6. So this is a little bit hard to think about, but what I'm going to do is going to put 1/2 plus 1/12. Wait, no. Okay, so this is 2 over 2 minus 1 over 2. Wait, let's see. Okay, this is actually kind of difficult. Let me rethink this. Alright, so what I'm going to say is minus 2, minus 4, minus 6, minus 8, etc. is just going to be it's just going to be half of the harmonic series, which itself diverges. And 1 plus 1/3 plus 1/5 plus 1/7 also probably diverges. So, okay, let's see. What can I do to solve the alternating harmonic series? Well, let's see. This is a very tricky question, actually. So, I think we can solve it using telescoping, though. So, we have 1 minus 1/2 is equal to 2 minus 1 over 2. We have 1 times 2. We have 1/3 minus 1/4 is equal to 4 minus 3 over 3 times 4, and so on and so forth. So what's actually going to happen is this is going to be 1 over 1 times 2 plus 1 over 3 times 4 plus 1 over 5 times 6 plus 1 over 7 times 8, and so on and so forth. And hopefully I can figure out how that telescopes pretty quickly. So I'm pretty sure this converges. Just to be sure, I'm going to write it down. So AN is just going to be equal to, well, this is A1, this is A2. So this is just going to be equal to 1 divided by 2n times 2n minus 1. So that means AN plus 1 divided by AN is equal to 2n times 2n plus 1 divided by 2n times 2n minus 1. This is going to be 2n plus 1 over 2n. No way this diverges. Oh, I think I did this the wrong way. Wait. If AN plus 1 divided by AN is greater than 1, that implies that AN plus 1 is greater than... No, that's wrong. That's definitely wrong. So let's see. We have 1 over 2 plus 1 over 12 plus 1 over 30, so on and so forth. And so, oh crap, I'm dumb. Very clearly. Okay, so this is going to be 2n times 2n minus 1 times 2n plus 2, 2n plus 1. But wait, that makes it even greater. Okay, let's see. So, does this diverge? No, it can't be. But, oh wait, no, I had the whole thing reversed. So, this next one is 12/30 of the original. Oh yeah, this would be inversed. Okay, so this doesn't diverge. So we have 1, okay, plus 1 over 56, plus 1 over... Okay, this is definitely a tricky question. So, I'm gonna say this definitely converges, but I have no idea to what it converges to. So, let's see. If I can figure it out within this time span, it would be great, but my guess is that I probably can't. So, I'm gonna make one last desperate attempt. This is just a half of 1 plus 1/6 plus 1/15 plus 1/28. Okay, does anybody have any ideas of how to solve this converging series?